So I'm Marco. I'm representing here the group. The work has been done by a master student of mine, Botton, and also from a PhD student, Aluiso, Wrasse, and the other colleagues. They come from the mechanical engineering department, to which we have close collaboration. So let me give you the motivation of this work. In many branches of industry, we have what we call like two-phase flow. That means you flow in the same pipe or in the same vessel different liquids or gases, or gas and liquid, which is quite common in the petroleum industry. This work has been supported by Petrobras, as the national oil industry in Brazil. And therefore, we are very much interested in looking into this kind of flow. And of course, reliable sensors are necessary for flow monitoring. And the ultimative aim is probably doing online measurements in real applications. But what I'm talking today will be more like pilot plant measurements that is a more controlled environment. But even though very important also for flow models development and also flow models validation, which is as important as the measurement itself. So here what you see is two common types of two-phase flow. We call that sludge flow. There are pockets of gas flowing in between the liquid, or quite common is also stratified, where you don't have enough momentum for the liquid to slip off, let's say that way. Sensors have been around quite a lot. How can I make the movies moving? That's good. So flow tomography is been around for a while. So what we're seeing here is, of course, a high-speed camera measurement. This is a very, let's say, well-behaved flow. And what you see here, there are two sensors. They are not the sensor I'm talking today because they are intrusive ones. So also in the medicine industry, don't like to put things inside pipes. But this is a very good, what I used to say, like flow microscope. So we can really see the details of the flow. So the gas is being shown here in red and the liquid in blue. And if you go a little bit further, I cannot move that, but the movie is moving. So now we have a more like turbulent flow. So you still can see a few details of the small bubbles. We cannot detect them very accurately, but we can see that. That's what we call the wire mesh sensor. It's a good reference, but it's not good for industrial application at the end of the day. So we come up with a more simpler principle. We call that direct imaging sensor. It's based in also further works what we call electrical capacitance tomography, which is very similar to electrical impedance tomography, which is also used in medicine. So, but the approach here is a little bit different. So we don't measure the capacitance in between the electrodes, but it's useful way to do it. We have a transmitter electrodes and a number of receiver electrodes, and we measure the capacitance in between those two. Of course, this area here, it goes a little bit deep into the pipe, but we are not measuring the full inside of the pipe. There's some instrumentation here, of course, to measure the capacitance. We have seen many different types. We have used here just a simple transimpedance amplifier. Could be also charge discharge technique and so on. So the advantage here is non-intrusive, and we can do that very fast. I can measure each one of those capacitance here up to 100 kilohertz frame rate. If you think that the flow is also a very dynamic object, we need to do very fast measurement. The accuracy is not so important here, but more the velocity. We have presented this last year and also published that in IEEE Sensor Journal. So just to have an idea, that's kind of image, a cross-sectional image, and if you cut the flow in the middle, so the axial cut of this flow, you would see that there's what we call that slugs, And this is what the sensors represent, basically a kind of planification of the pipe with what we are seeing. That's the work done so far. And now what I'm presenting today has to do with kind of imaging reconstruction. Basically, in the previous paper, I said I don't need any image reconstruction. And in this paper now, I'm saying, okay, let's do some image reconstruction to have more details. Basically, I didn't say that, but there is some details which are there. We have a number of data here which could be further processed and where we can try to get some more information. So, very classical way doing this, we know that the forward problem is quite nonlinear, but we linearize that in a very simple way. What we call here is the sensitivity matrix. We generate that matrix by FEM simulation. That means a perturbation approach is used. We put some perturbation here and see how they behave in the capacitance measurement. And there is I have to solve this inverse problem, and a very simple way of doing this is using linear back projection. There is much more sophisticated ways of doing this, iterative methods and so on, but this one is very fast, and that's one thing that we'd like to stay, but further works could be also in that direction. Okay, that would be for the image, but the title of the paper is velocity measurement. So that means I'm using also another principle which is quite common, that's the transit time measurements. If you have a structure going on the upstream sensor and then to the downstream sensor, you got two signals, they are time shifted. If I measure the time shift, and normally we are using cross correlation, there are also other methods. And I know the distance between the two, I get the velocity. Of course, this is the structured velocity, not the real gas velocity. So I have multiple electrodes. That means I can cross-correlate one to each other in each one of the planes. So I will have then a matrix of 64. In this case, we have 8 electrodes in each plane. So 64 velocity measurements. But I still have to model what velocity I'm measuring. So in the model comes in the other forward way I did with the images. The problem is non-linear, but I'm linearizing the problem, saying that the true velocity here would be that u here. It is related with the velocity I'm measuring to also a kind of sensitivity metric. We call that weighting metric. And when I cross-correlate adjacent electrodes, basically I'm looking at the velocities on close to the border. Of course, I can do that for all the 8 electrodes. I have to get the information around the pipe. And if I cross-correlate opposing electrodes, I'm getting some information in the middle of the pipe. So, of course, I can extract some information of the whole cross-section. The same way I did before, I use linear back projection, not the most efficient way of doing this, but very fast one. And, there is the square here should be a dot, but at the end, the true gas velocity, I would get multiplying the velocity by the void fraction, what they say, that is the image I reconstructed before. So that is basically how is the phases are distributed over the cross section. Okay, we have done some simulation with synthetic data. So we generate square bubbles with different velocities and use them to solve the forward problem, and then again the inverse problem. Being synthetic data, of course, we are a little bit biased, but it's good to see that we can still, although the image is very smeared, that's the result of this the simulation and the measurement, but we can also at least recognize that we are measuring something which is visible. So have done that, then we went to the test bench we have in our university, where we generate two-phase flows that I showed you before the measurement. And this is just an example of that velocity distribution. If I integrate that over the cross-section, and then I get the reference flow rates, which of course are still quite far away from being ideal, but it gives me the confidence that we can keep doing our research in that direction, because online measurements of flow rate in two-phase flows is a quite difficult thing, and this seems to be a rather simple way to do such measurements, at least for the gas phase. Okay, I know I'm competing with lunch, therefore I will finish. So I think I've shown you that using sensor data processing, we can extract more information than the information we have beforehand. And doing basically peripheral measurements, we can still have some information on the flow velocities based on this tomography principle. The results give me some confidence to continue doing this. As I said, some reconstruction algorithm, a more complicated reconstruction algorithm could be used, and the next step would be to combine it to measure the liquid velocity as well, for example, with a Venturi meter. Okay, I'd like to acknowledge some support, financial support, and also thank you for your kind attention.